Hello everyone, welcome you all to this session of setting up a crash model for radios using HyperMesh. And myself, I am Prashant here. I am from Altair India office. So the objective of this session is, uh, as it is there in the title also, to understand how to set up a crash model for radios using HyperMesh. So here what we'll be doing is we'll be having just a mesh model without any other data. So from there we'll start on putting up the information which is as required by the solver and as it is required by our load case, and finally we'll end up in a runnable deck which we can solve it in radios. So that is the main objective here. And as we go along, we'll also try to understand some of the basic concepts of the radios. This is not a solver training. This is not a radios solver training. This is basically a HM radios interface training. So here the stress is more upon how to set up the model rather than understanding many of the solver basics, which we'll take up in a separate session. So before directly jumping onto the actual activity of setting up a deck, here I have some slides which will put more light on the radios block solver, which we are trying to understand also to some extent, and our entire activity will be revolving around these topics. So this is a more generic slide where I'm trying to make you familiar with the different softwares what we have under the Altair umbrella. So in the pre-processing category, like there are tools like HyperMesh, HyperCrash, HyperForm, MotionView, and AccuConsole. So all these are pre-processor for different applications, and we have the HyperView and HyperGraph as the post-processing tools. And as you can see, like there are different solver codes which are available here. It may be static or nonlinear implicit, nonlinear explicit, thermal and CFD and MBD. So the interface, what I'm talking about, it falls under this category, in the nonlinear explicit category. And solvers mainly called by the names, like all these codes can be called as radios, which has different capabilities here. And in the CFD, radios also has some CFD capability, but apart from which we have a separate code for CFD application, which is AccuSolve, and for MBD application we have the MotionSolve. And apart from which, one other big area is optimization. And we also have the data and process management tools. So coming to the application field, this is one of the biggest area where it can be applied for structural mechanics, something like a crash event, what you are seeing it here. And Redis can also be applied for FSA simulation, fluid structure simulation. Here you are seeing a bird scenario where the bird is a fluid and it is interacting with the structure here. And Redis is also used in the area of metal characterization. And radio has rich property and material library for composite application. And again, coming to automotive or aerospace, it can be applied for safety application, where Radius has rich libraries of automotive and aerospace dummies from the humanetics. And here we are trying to understand the interaction between the dummy and airbag, seat belt, seat, so all those things which comes in the safety. And you may be having different barriers also, so all those things comes under safety. And if you're using HyperForm, in the HyperForm it uses radios to solve that forming jobs, so in the manufacturing simulation. And as I mentioned earlier, like radios also has some CFD capabilities, which we are seeing it here. But what we are discussing today, it is applicable to structural mechanics and maybe something related to safety also, but it is majorly on structural mechanics. So all the properties, all the materials, all the contact, all the connections which I discuss here, they'll be mostly applicable to the structural mechanics category. So the idea is, as we go along, I'll try to show you how to set up maybe an impact case So that is what the idea is. So coming to the application, if we talk in the automotive perspective, like when we're calling it as structural mechanics, it may be a regulation driven. We do a lot of analysis calculation in this area, where it is linked with some of the regulation. Regulation may be European, American, or Indian regulation. And as you saw, like in the automotive also, there may be a fluid tank sloshing scenario, which comes under the FSI category. And people also do some low-speed impacts in cases to study the robustness of the structure. So these are some of the typical analysis cases which I have listed it here. And in the general engineering, the cases are drop test is one of the very wide area in the general engineering, and there also people do some impact analysis. It may not be very high, as high speed as we do it in the automotive application, but definitely like the case goes into an impact case. And apart from that, fit analysis is one more big area, and quasi-static analysis or a slow loading analysis in the general engineering category. And some people also simulate the mechanism where they will be looking for some of the stress strain results. They do the mechanical simulation using the Radioss explicit. And in general engineering also there will be FSI cases. So this is very brief on the application context. So when we call it as an analysis file, a file which is runnable, so what all it can contain or what all it should contain. So this is very important for us. Yes, definitely it will contain nodes and element, and as of now the model which I have, that also contain only nodes and element. But apart from that, it will be requiring material, it will be requiring property. So if I stop here, then till here it was only the nodes and element, and when I put the material and property to it, it will become a more lively. So it is so its definition is more complete in that regard. So when I put loads, so you have a component, so we are putting the duty loads on that one. So it is moving towards the analysis case. Earlier we had just the more complete model. Now it is moving towards the analysis case. So apart from the loads and boundary condition, one more important thing is contact. So here, since we will be dealing with many components, so here the interaction between the components are very important. So we require contacts, and we require control cards to control many of the parameters, maybe controlling the output or controlling some of your run parameter or controlling some behavior. So for all those things you will be requiring control cards, and of course output requests. So we are doing the analysis, so we expect some results, and we need to specify what are the results we need, and we have to put that in the output request. So this, I feel, some of the very important things which analysis deck should contain. So as I mentioned, as of now we have only the nodes and elements. So we have to add all these parameters to our file. And how we have to add? We have to add in such a manner which is as required by the solver, which is as required by our Radioss solver. So we'll try to understand how we will input this using HyperMesh. So that is our objective. Okay, now some basics regarding the solver. So the material, I'll be trying to use one material which I'll be trying to use is elastic material, which is a very simple material. It is a linear material, and normally we don't use this in the explicit analysis unless we feel like during its operation it will not get into a yield mode, or in some situation like we'll not be much interested in the results of those components. At that context also we use that. It requires the basic parameters like density, Young's modulus, and Poisson's ratio. So the second material, and a very famous material, is a Johnson-Cook material. So this is the basic non-linear material. which can be used for metals and plastic. So apart from the first three parameters, which we density, Young's modulus, Poisson's ratio, which we have seen in the earlier material model also, the extra parameter what it requires is it requires the yield stress of that particular material, ultimate stress of that material, hardening parameter, and hardening exponents. So these are the parameter which this material model requires. So we will be using that as well. And this is the most comprehensive material and very widely used in the automotive application. So here, apart from the first three basic parameters, we'll be defining the stress strain curve in the material model. So this curve is between the true stress and the plastic strain. This you may be having some testing data as a stress strain curve. So those data with a proper with the proper correction, you can use that stress strain curve here as a true stress and plastic strain, which is a very good way of defining the nonlinear material model, and we use it very extensively. So apart from this, maybe like if you have fabric, you can use the law 19, maybe for seat belts and airbag, and Ogden if you have any rubber parts. So in my model, I'll be using this first three materials at different locations. So we'll see that. Apart from that, like Radioss has a rich library of materials under a different category. As you can see, like in the elastoplastic, there are many, and orthotropic. If you have any orthotropic material, and if you have any foam which falls under the viscoelastic, and if you have any rubber which falls under hyperelastic. So it depends on your application and also on the data which is available with you. We pick the material loss. And coming to the properties, in the 1D elements, we have the beams and spring, and of course the trusses as well. Here I have listed only the beams and springs. So beams, we use it for some standard structural sections, and sometimes for some connections. But springs are the one which are very widely used for different purposes. As you can see, like we can use it for suspension, damper, bolt, weld, glue, and many more. So this is the general classification. But if we talk in terms of radius, then in radius, like we call the beam as type 3, and in the springs there are many varieties. Spring 4, 8, for different application, which we will see. Like I have one more slide on that one, which is more detail in this regard. And the 2D elements normally for BAW and body in white, door in whites, or some injection molded plastic parts. So you can use the 2D machine, which you may be already knowing. If I talk in Radioss context, so this is the one widely used general purpose shell. Apart from that, if it is orthotropic, maybe something like a fabric, then it is a orthotropic shell. Or if you have any composites, then it's a composite shell. And we have the sandwich as well. But this is the one which is very widely used in all over maybe panels and brackets. For solids, like if it is a casting component, we mesh it with the solid elements, and in Radioss context, so this is the one which is very widely used, the general solid. Okay, so this is a more detailed slide on 1D elements, as I mentioned earlier. So for the beams, as I mentioned, you can use it for some standard sections, and trusses for some suspended chains or rope. And talking about the different types of spring, type 4 spring, it's a combination of spring and damper. You can use it as standalone spring also and standalone damper also. So, which is very widely used in the suspension system. So this type 4 is a spring which is very widely used in suspension systems. And we have one more spring which is type 8 spring, which is normally used for joints and some measurement application, some location where you require measurements, like say like you want to measure the intrusion, in a very accurate way. So you can put this spring, and on this spring you can measure the intrusion. And type 12 spring is a pulley spring, so which can be used for some anchoraging purpose, normally used for maybe a seat anchorages, one of the very good example. So where we use this pulley spring, type 12 spring. And type 13 is a beam type spring which has many application, like when we create the spot weld, when we create a glue, when we create a bolt or weld line. So in the background, system automatically creates this type 13 spring for us. And apart from that, if we have a very detailed suspension property, then we can try to use this type 13. So we find, as you can see, like in radios at many places for many different applications, we use this spring, but you have to selectively pick the spring depending on your application. That is the reason you have try to classify this depending on the application, rather than going about in detail regarding its property or how you create it. So this is one basic information regarding the 1D elements. And coming to the contact, for all your node to surface or self contact or some contact which you put it for the complete vehicle, something like this, that contact will be a type 7 contact. Or like here you can see like a impactor is hitting the bumper. Again, it is a type 7 contact. So this is our very widely used contact. But the limitations of this type 7 contact is it cannot identify the edge to edge or edge to surface contact. So for that reason, we have one more contact which is this type 11 contact, which is between edge to edge, as you can see it here. But our global contact will be type 7 contact. At some selected location, we can create this type 11 contact, because type 11 contact is expensive. So we don't normally use this type 11 as a global contact. So our global contact will be type 7. And wherever there is a necessity of using this edge to edge, where we use this type 11 contact. So apart from this, so these two are a sliding type of contact, type 7 and type 11. So we have one more fixed or freeze type of contact, which we call it as a type 2 contact. So when we have that type of scenario where we need to fix or freeze maybe two panels or two components, we use this type 2 contact. Apart from that, whenever you create a spot weld or glue, these are mesh independent connections. As you can see here, this is a case of a spot weld where it is this spot element is not directly connected to any of the node. So essentially, when you're creating a spot weld, it will create a spot weld element and will establish a relation between this top and this bottom panel using a contact. So that contact is type 2. So this is what a system creates when you create a it means this is what HyperMesh creates when you create a spot weld. So in the loads and boundary condition, here I have tried to classify this loads and boundary condition depending on the application. So the first two are the constraint condition, and all the next loads what you are seeing, you can use one of these loads normally for the quasi-static analysis. So when we call the analysis quasi-static, our loading will be one of these. And when we call it as an impact analysis, or when it is a drop test, the loading will be always initial velocity. And gravity loading, normally we don't use it as a standalone load, but we couple it along with impact as a combined loading. So this is the classification of loading as per its application. So in our model, which I'll be demonstrating, I'll try to use one or two of these loadings. Okay, now since we are talking about the explicit analysis, I would like to bring two important things here which we need to monitor and control. So the first one is time step. Here I'm not explaining the concept of time step. While meshing itself, we are insisted to maintain the length of an element. So yeah, like you may be having the guideline like the element length should not be less than maybe 5 mm. That is because if you see here, like the time step is governed by that length and a material parameter of that component, which C is square root of E by rho. So this is the formula for the element time step, and nodal time step is calculated by the nodal mass and nodal stiffness. And normally the nodal time step is higher than the elemental time step. So for us, the important thing is, like, first thing while modeling, you have to follow that guideline, and the element should not be less than a particular length which you have already fixed. And we insist the solver to run with one particular time step. See, like now, you may relate this number, it is 1 e power minus 6, 1 microsecond. You might have done your meshing with a particular time step. So here I'm putting the same number. So I'm not getting into the concept of time step. And one more thing is hour loss. So hour loss is a phenomena which we need to control. Again, I'm not explaining what is hour loss, but I'm just telling like it is a phenomena which we just need to avoid or control, which occurs in quad and hexa elements. So how we control that using better formulation. So here I'm directly giving a solution in terms of formulation. So if you're using shell, it is advisable to use the formulation I shell is equal to 24, and if you're using solids, it is advisable to use I solid is equal to 24. So these are the recommendation. And while using this recommendation, be bear in mind that I'm assuming that your mesh is not very coarse. So to say, like your mesh average length is say about 8 mm, and maximum length of an element maybe 10 to 11 mm or 12 mm. If you have very coarse mesh, then it may not be advisable to use this formulation. But normally in our automotive meshes, like we'll follow a global size of 8 mm. So you can use this formulation, which will control or avoid these hour-less scenarios, which is bad for us. So these are two important things which I just touched upon. And in Radioss, like our starter, we have two file format. One is starter, and another we call it as the engine. So starter has entire information regarding nodes, element, material, properties, contacts, output request. So all the things which you can think of, which you have already created in your model. So all these things will be there in the starter. So then what the other file contains, which is engine file. So if you see here, so this I'm calling it as a starter. And what this engine file contains. Engine file contains the information something like the duration of the run, how long your run has to run. So here it is 120 millisecond. And when run is progressing, we will be requiring the animation at regular frequencies, so that if an impact is happening, we want to see that in a progressive manner. It is not that you have only maybe two files, where in the initial the vehicle is just stationary, and in the end file it is already impacted. So we don't want that scenario. We want to see this impact happening in a progressive manner. So we have to extract the result at frequent intervals. So that is what we are doing it here. So I'm extracting the result at every 5 milliseconds. So for 120 millisecond, I may be having some 24 files. So I can see that deformation at a progressive manner. So not only the deformation, so all my results. So here I'm requesting the results for plastic strain, wall meshes stresses, some vectoral components, some contact forces. So all these results will be available for me at a regular interval of 5 milliseconds, 5, 10, 15, 20, like that. And as I mentioned, like I'm imposing a time step of 0.5 microsecond here. And so here I was telling about the animation frequency, but apart from that, I'll be interested in a lot of graphical data in terms of the maybe energies, forces, so all those things. So here I'm specifying it will create a file which is the T file, T01 time history file. So that will contain that graphical output what I have requested. so that output will get updated at this frequency. So if I specify this frequency maybe a very big, then my graph will not be very smooth. So we try to keep it a small value, so that maybe sometimes we have a relation between these. So like normally guideline is we keep it maybe 1/10. In this case it is 1/100th of this value, so that we have more points for the graph and we can get a smooth graph. So it is for that reason. So this is something which I try to explain regarding the engine file. So if you see the file format, as I mentioned, we'll be having the starter file. So when you start your solver, first the starter will run, and it will generate its own out file, which will look something like this as you're seeing in the background. It will generate a binary restart file. So our starter file will have a format of 4 zeros .rad, and its out file will be having a format of 4 zeros .out. So if you have any logical errors, so to say, like you have created a part which doesn't have a material, or you have created a shell material which doesn't have a thickness, or you have created a contact which doesn't have a master segment. So these type of logical errors will be listed in this out file, which is very easy to read from it and correct it, which will be very straightforward. So once that, this you can also call it as a check run for your model to check the consistency and of your model. So once it is done, the solver will start the engine. So engine format is 301.rad. So as soon as the engine starts, it will create its own out file. So this is very important to us in terms of monitoring the run, how it progresses. So it will generate the animation file as per the frequency what we have specified. It will create A01, A02, A03, so on. And it will create only one time history file which will keep on getting updated as per the frequency what we have specified. So this will create a different animation file itself for the frequency what we have specified, but this will be a single file, but it will get updated as per the frequency what we have specified. So as I mentioned, like we'll be keep looking at this file as the starter run is over. After that, we'll be keep looking at this file to understand the status of the run. Okay, so this is a simple a slide which shows the procedure how to run a Radioss job if you're running it in Windows. If you're running it on a cluster, the procedure will be different. But this